Hello and welcome to this video for Chemistry 30, the electrochemistry unit. In this lesson, we're going to start looking at some applications of electrochemistry. One big one being batteries. Okay. Now in chemistry, we actually call a battery a cell. And the most common type of cell that we're going to talk about today are voltaic cells. So voltaic cells are a type of electric cell that converts chemical energy into electrical energy. So essentially what's happening is we're going to have a chemical reaction transferring electrons, right? Which sounds just like a redox reaction. So during that chemical reaction, the electrons are going to transfer from the substance losing the electrons to the substance gaining the electrons through an external circuit, through a wire, okay? And we separate the two half reactions into containers called half cells, where there's a electrode material, usually a metal, in the solution, and then a solution of those ions that are surrounding that. Now I have a video here that I'll put in the comments that shows a nice diagram of what a voltaic cell, an animation of what a voltaic cell really looks like. Now, we have, like I said, not only the electrons flowing between the two half cells in a wire that separates them, but the ions also move between them as well, and we'll look at that in something called a salt bridge. So the electrodes are made of good conducting materials so the electrons can flow. Usually it's the metal of the solution, or it can be inert like carbon or platinum. And the solution is called an electrolyte because it contains ions that will conduct electrical current. Okay, so it usually is going to be ions that are reacting, but it could also be an acidic solution like battery acid and things like that. Now, this is where the chemistry part comes in. Remember our saying, Rallio the ogre. We can, or Leo the lion says gur. We can redo that to say Rallio a. So Rallio a, and if I go down here, oh, it must be on the other slide. Rallio a the ogurk. Okay, what the a stands for in Rallio a is that where oxidation occurs, where the reducing agent reacts, that is called the anode. Okay. If the anode is a metal that's actually undergoing an oxidation reaction, it's going to produce ions. And what's happening in that reaction, anytime you have a reaction, this kind of goes back to even Science 9, learning about reactions. Your reactants get used up and your products get produced. Okay? So what that means is that if your anode is a metal that's actually reacting like copper, losing electrons, the copper metal is going to start to lose mass. It's going to get smaller and smaller and smaller as it reacts. But the concentration of the copper ions being produced are going to increase. So reactants always go down when they're solids. We talk about their mass. And products always go up when they're ions. We usually talk about their concentration. Now, copper actually makes a blue color in solution. So as this cell operates, it becomes a deeper blue color, because again, copper ions are being produced. When something is being produced, there's more of it as the cell operates. Okay? So mass of reactant gets lost, concentration of product increases. All right? That's a lot of questions that you'll see come up on diploma style questions where they ask about the color, the mass, and things like that. Now, the anode is labeled as the negative electrode because that's where the electrons are leaving the system, traveling to the cathode that's gaining the electrons. So when you have a battery or a cell, wherever the electrons start is labeled as the negative electrode. However, as the cell operates, we're building up positive charge. The electrons are transferring over to the cathode, so they're going to be gone. And what's happening is we're building up positive ions. So there's actually a net positive charge that starts to build up on the anode as the cell operates, which means any anions in the solution, which are negatively charged ions like nitrate, for example. If you have nitrate in the solution, that's an anion. The anion is going to be attracted to the anode as the cell operates because, again, chemistry speaking, it starts to build up a positive charge as it produces positively charged ions, and the electrons are leaving, being gained at the cathode. Okay, so our other half cell is, again, the cathode. And so in our saying Ralioa, it's the ogerk. So the oxidizing agent that undergoes reduction by gaining the electrons lost from the anode is happening at the cathode. Okay, the cathode. And the cathode is, because it's where the electrons are moving towards, is the positive terminal. Now, if the cathode is made out of metal, so let's say I have zinc ions, for example, and my zinc ions are gaining electrons because reduction would happen at the cathode, I would make zinc solid. So now when we're looking at what's happening in terms of the reactants and products, my reactants are going down and my products are going up. For every reaction, that's what's happening. You're using up reactants, you're producing products. So the amount of reactants go down, the amount of products go up. This time, my product is zinc metal, or my reactant, sorry, is zinc ions. And my zinc ions, therefore, their concentration is going to go down. Now, zinc ions don't have a color, but if they had a color, the color would be getting lighter because there's less and less and less ions. But my zinc metal is being produced. So the mass of the zinc electrode is going to increase if that electrode, again, is a metal. Notice how it says if the cathode is a metal. Because, again, the cathode and anode don't always have to be a reactive metal. It can also be inert, like carbon or platinum, which we'll look at some examples. Okay, so if it's a reacting metal and that metal is being produced in the reduction reaction, obviously as a product, its mass will increase, okay, as the ion reactants decrease. It's labeled, like I said, as the positive electrode. However, in terms of what's happening chemically, as it's gaining electrons and losing positive ions to make the solid metal, it's actually building up a net negative charge, okay, because electrons, again, are negative. So what that means is any cations in the solution, any positively charged ions, like, again, zinc ions, which are positively charged, they would be attracted to the cathode because the cathode, again, is starting to build up a net negative charge as it's building up those negative electrons, okay? So in summary, Ralioa, the ogerk, okay, the reducing agent, the strongest reducing agent in your solution is going to lose electrons undergoing oxidation at the anode. The electrons are going to transfer from the anode to the cathode. The cathode is where the oxidizing agent, the strongest oxidizing agent in your solution, gains electrons undergoing reduction. Okay? The cathode is labeled positive, the anode is labeled negative. Now, even though they're labeled as negative positive, in terms of chemistry, they're actually building up the opposite charges. The anode is becoming more positive. So any anions in the solution are being attracted to the anode, and any cations in the solution are being attracted to the cathode, okay? And the electrons, again, are flowing from anode to cathode. Now, we're going to draw diagrams of cells, Voltaic cells, but before we get into that, there's another little topic that we have to talk about that is part of cells. So, like we said, the electrons flow from the anode to the cathode, but ions also need to be able to move, the anions and the cations, like we talked about. And those move through either a salt bridge or a porous cup. A porous cup is basically just a ceramic cup that you can put inside of a beaker that you separate the two half solutions in. And it's porous, so it allows ions to transfer through slowly, but the solutions don't like really quickly mix. It keeps them separate. Okay, so we need to allow the ions to move in order to allow the charge to not build up, in order to allow a complete circuit flow of electrons and positive and negative ions. Otherwise, the charge will build up and it'll oppose the movement of electrons. So what we're going to look at that is part of cells also are something called reduction potentials. Reduction potentials are the ability of a half reaction or a half cell to attract electrons. They are measured using a voltmeter and measured in the units of volts. Okay? Now, the table in the data booklet actually has these numerical values assigned to them that we haven't really looked at yet, but those numbers are the reduction potentials, okay? Now, they are all arbitrarily assigned to a standard. So something that's been set as 0 and everything else is relative to it, and that is hydrogen. The hydrogen half reaction has been set at 0. And then everything above hydrogen is positive, everything below hydrogen is negative, and it again shows you how strongly it wants electrons. So if we look at the data booklet, there's hydrogen in the middle at 0. Okay? Now, you could be given a sample diploma, here is a sample diploma question, a question you could see on the diploma or on your tests or quizzes, where it says that silver instead was chosen to be the standard. How would it affect cadmium's half reaction? So what you're going to do is find silver on the data booklet, and you're going to figure out what do you need to make that become 0. Okay? I would have to subtract 0.80 to make it become 0 because it's positive 80. So I'd have to subtract 0.80. I'm going to therefore look at my cadmium half reaction and apply the same change. So right now it's negative 40, negative 0.40. I'm going to also subtract 0.80 from it. That's the change I have to make. Not only if I make silver the standard, it becomes 0. Everything else shifts by the same value. Okay? So cadmium would become negative 120, and that would be the answer to that question. Okay, so if you're assigning something else as the standard, you're figuring out how do you make it become 0, and then apply that same change to another half reaction. Now, how do we find the voltage or predict the voltage of a voltaic cell? We have the following formula. Your E net equals the E naught of the cathode minus the E naught of the anode. Not just means where the voltages are at standard conditions. And the data booklet explains standard conditions are at, I think, 1 mole per liter solutions. So concentration can affect the voltage. We're not going to get into that in Chem 30, but it actually, it depends on the relative reaction of the concentration to the reactants as to how it affects the voltage. But the E values are independent of the number of electrons transferred. Okay, so if I have to multiply a half reaction to make the electrons balance, that does not multiply the voltage values. The voltage values are independent and they stay the same. Okay, cathode minus anode. Now, if you get a positive value, then that means your reaction was spontaneous. If you get a negative value, that means your reaction was non-spontaneous. So this also helps us predict the spontaneity of our cells. And voltaic cells should always be spontaneous and positive. Okay? There's another type of cell we'll look at in the next lesson where they're always negative. But if they're positive and spontaneous, they are a voltaic cell. So let's say we have the following mixture. We have zinc solid in a solution of copper sulfate. So if I list everything that I have as it would appear on the data booklet and find what they are, I just gotta grab my data booklet. So zinc is the Ra of a solution. Of course, the water could also be an Ra, but you'll find that zinc is obviously further down on the right-hand side. So that's my strongest reducing agent. And my copper is the strongest oxidizing agent. Now, sulfates can also be an oxidizing agent with hydrogen ions, but there are no hydrogen ions present. They can also be an oxidizing agent with water, which is present, so we can list it there like that. But again, my copper is going to be my strongest oxidizing agent. So my strongest oxidizing agent is going to undergo reduction. And again, you could even write, rather than writing that, you could even write your saying ogerk. Just make sure you remember what everything in that sentence or that term means, ogerk. This means my oxidizing agent is undergoing reduction by gaining electrons, and this is my cathode half reaction. So my copper 2 plus, now it doesn't actually ask us to write the reactions, but I'm going to do that just to practice it anyway. So this is my cathode, okay? So the half reaction of copper gaining 2 electrons, now I need to find that in the data booklet, there it is positive 0.34 volts, okay? My reducing agent losing electrons undergoing oxidation at the anode is my zinc metal. My zinc metal will lose 2 electrons, forming zinc ions. Okay, so the electrical potential of my anode, my zinc half reaction, is negative 0.76 volts. Now again, my electrons here balance, but if they didn't and I had to multiply either half reaction, you would not multiply the voltages, okay? So I'm not even going to write the net reaction. I'm just going to figure out what is the net voltage. So again, it's cathode minus anode. And I could put knots for all of these. Not that it really makes a difference, but so my cathode is positive 0.34 volts, and I'm going to minus my anode, negative 0.76 volts, okay? So if I do that calculation on my calculator, 0.34 minus negative 0.76, we get an answer of 1.1. Now I need to put positive in front of it, just like we did in the thermochemistry unit, because positive again tells us that it is spontaneous, so we want to show that positive. And I need, because I'm adding, my sig digs are decimal places. I have 2 decimal places, so my answer needs 2 decimal places. So my answer will be positive 1.10 volts, and that again shows us that this is a spontaneous reaction taking place in this cell. Now let's look at something called shorthand notation. So shorthand notation is a quick way of showing what's happening in your cell, okay? There is 2 horizontal lines that separate the 2 half cells. Everything on the left is always the anode, and everything on the right is always the cathode, okay? The ends are your solid electrodes. So I have a zinc solid electrode and a copper solid electrode in this cell. And then separated by a single line in each half cell is the ions that are surrounding that metal. Now you can also read these as what's happening in the reaction. My zinc solid is becoming zinc ions as it loses electrons. My copper ions are becoming copper solid as they gain electrons, okay? But when you have a question like this, you can list again what you have present, find your SOA, your SRA, and those are, again, the SOA is the cathode, the SRA is the anode. Now this is a simple cell like actually the one we just looked at, the zinc copper cell, okay? But you could have a little bit more of a complex cell. Okay, so as I was saying, you could have a cell where the material that is being oxidized or reduced, either or, are are ions that are not forming a solid material, and that's when we use inert electrodes, okay? So the zinc is still the same like before, but look at what we have on the cathode side, okay? I have carbon solid. That is not a solid form of chromium, right, in this solution. Carbon is just an inert electrode. So that means it's not actually a reactant or a product. It's not actually part of the reaction. It's just there to facilitate the flow of electrons because it's conductive, but it's not actually part of your reaction. The ion dichromate and hydrogen, it has to be acidified, they are reacting to produce chromium 3+ ions in their half reaction, okay? So all of the ions surrounding the inert electrode are part of the reduction half cell or the cathode half reaction, okay? Notice how there's commas between these ions. So again, like I said, the single line separates the states or the phases between the half cells. The double line represents the separation between the two half cells with the porous cup or salt bridge. And then any comma represents species that are in the same phase. So all of these ions are aqueous surrounding the solid copper or solid carbon electrode, So that solid carbon electrode, that again is with a single line, and all of these ions have commas between them, okay? So that's also part of drawing or representing, your shorthand notation. And like I said, it's always anode versus cathode. Anode on the left, cathode on the right. Now let's say you're asked to draw a cell. There's a lot of information you have to give. You have to label the cathode, the anode, the positive and negative electrodes, terminals mean electrodes, the electrolyte solutions, the direction of electron flow, cation and anion flow, that reduction, oxidation, and net reaction, including the net voltage and spontaneity. Okay, so lots of things to label. So obviously questions like these take a little while. Now what I have here is aluminum in a solution of aluminum nitrate. So aluminum nitrate has been dissociated into ions that have a comma between them because they're in the same phase of the solution. And that is my anode side. And on my cathode side, I have nickel nitrate dissociated into nickel and nitrate ions, and that's surrounding an electrode of nickel. Now, like I said, this is my anode, but you could, again, go through and list everything that you have present, and you would find your aluminum solid is the strongest reducing agent. But your strongest reducing agent is always going to be on the left, the anode of shorthand notation. And then your strongest oxidizing agent is going to be the ion of the cathode half reaction, okay? Again, you could list everything, find them in the data booklet, and still, like before, find your SOA and your SRA. So my oxidizing agent is going to gain electrons undergoing reduction at the cathode, my positive terminal. Okay, actually, yeah, I'll do the half reactions first and then we'll draw the cell. So I have nickel ions that are gaining 2 electrons to make nickel solid. I'm going to write the voltage of this as well as my cathode voltage. So my nickel cathode, nickel is negative 0.26 volts, okay? My reducing agent that is losing electrons undergoing oxidation at the negative anode is aluminum solid. Aluminum solid is going to become aluminum 3+, and it's going to lose 3 electrons. So the E net of my anode is that aluminum value. Aluminum is negative 1.66 volts, okay? So to make my net reaction, I have to multiply this reaction by 3 and multiply the aluminum reaction by 2 to make the electron transfers balance. But notice again, I did not multiply the voltages. We do not multiply the voltages, okay? So I have 3 nickel 2 plus ions reacting with 2 aluminum solid atoms to form 3 nickel solid atoms and 2 aluminum 3 plus ions. And my net voltage, again, cathode minus anode. So my cathode is negative 0.26 minus negative 1.66 gives us positive 1.40 volts as our voltage. Now this reaction, again because it's positive, is spontaneous. Now to draw my reactions, and there's a couple of ways, or to draw my cell, there's a couple of ways you could do it. You could draw them as 2 separate beakers. So here's beaker 1, here's beaker 2, okay? And then I have 1 electrode in one of the beakers of the solution, another electrode in another beaker. I'm bad at drawing straight lines here. Now, which half cell you put in which beaker doesn't matter, okay? I'll just pick arbitrarily that this is the anode. Now, you're labeling it, right? So my anode is aluminum solid. That's what that solid metal is there. And in the solution around it, I have aluminum ions and nitrate ions, okay? That is my anode. So this will therefore be my cathode, which again is my positive terminal. And that would be my nickel solid with my solution of nickel ions and nitrate ions. Now, I need a wire connecting the 2 electrodes, and the electrons are always flowing from the anode to the cathode. Then you have something called a salt bridge, which is a U-tube, a glass U-tube, that gets connected between the 2 cells to allow the ions to move between them. I don't like that it looks like my electrons are in the salt bridge, because they're not. The electrons are moving through the wire, okay, the external wire. The salt bridge is to allow for the ions to flow between the 2 solutions. So like we said before, through this salt bridge, the anions are going to flow towards the anode, and the cations are going to flow towards the cathode inside of this salt bridge, okay? That's one way of drawing it, where you separate it as 2 half cells. And if you were to do a lab in class, this might be one of the ways that you build the cells. Now, there is another way of doing it as well, and this is a fully labeled diagram. The other way to do it is the porous cup method. And in the porous cup method, I just have 1 beaker with one of the solutions in it. And then we put I'm going to have to write this a little smaller. So there's my aluminum and nitrate ions floating around that electrode in that beaker. I then have this porous cup, which is like a ceramic cup that we put inside of the beaker. Okay, and it contains its own solution in it of ions, and you put the other electrode in there. So if that's my cathode, and again, it doesn't matter in the porous cup method, it doesn't matter where you put the anode and the cathode, which one goes in the porous cup, doesn't make a difference, okay? So I have nickel ions and nitrate ions floating around inside there. Now I still connect these 2 metals with a voltmeter. My electrons are still flowing in that direction, but now there's a little bit less space. Our anion flow is towards the anode, and our cation flow is towards the cathode. And those ions would just flow through the solution that we have right there, okay? through the porous cup, very slowly through the pores. Okay? So that is how you draw and fully label an electrochemical cell, including the half reactions and the net voltage. Okay? Okay, sample diploma question. So here we are given shorthand notation and the diagram of a cell. So remember again, your anode is everything on the left and your cathode is everything on the right. Now, I am given some key information here. I am given the directional flow of electrons, okay? So that means that number 2 has to be the anode because the electrons always flow from the anode to the cathode, okay? Now, number 2, anode, is therefore my zinc solid, and therefore the solution around the zinc solid are zinc ions, okay? This is the porous cup method, a little bit of a better diagram of the porous cup method, where you have the porous cup inside of a beaker that contains the other electrode in solution. Like I said, the porous cup doesn't always have to be the cathode. It could be the cathode or the anode. You have to look at details like electron flow, for example. Electron flow is a good way to determine where's the anode and the cathode, okay? So my cathode is this inert carbon electrode. All right, and the solution surrounding it are all of those ions listed there. So permanganates, manganese, and hydrogen. That's number 4, all of those ions, okay? And then 6 and 5 are referring to the ion flows or migrations is another word for it, okay? So number 6 would be the cation flow or migration, and 5 would be the anion flow or migration, right? The cations always flow to the cathode, the anions always flow to the anode. So if we were to answer this question now, the carbon electrode was what we labeled as number 1. The anode was what we labeled as number 2. The cation migration, movement of cations, was number 6. And the zinc solution is right there at number 3. Okay? So if you have cell shorthand notation and a diagram, this is how you go about labeling it. Now we're going to talk about some cells that are called commercial cells. So cells that we use in real life commonly called batteries. But a battery technically is when you connect 2 or more voltaic cells together. Now if you have them connected in series, one after another, then the voltage is the sum of the individual cells. Okay? So common dry cells that we have are the common type of battery you may think of, 1.5 volts and 9 volts and so on. Now they're a dry cell because they have a paste inside of them, not liquids as the electrolytes, okay? And they produce hydroxide ions, which makes recharging them impossible. I will have, I think, a diagram of the inside of a cell, a dry cell, and what it looks like. Rechargeable batteries are things like lithium-ion and nickel-cadmium batteries where they don't produce hydroxide, so they are reversible. A lead storage battery is a car battery, okay? And it involves lead and acting as the anode and lead dioxide acting as the cathode in a solution of sulfuric acid. There's 6 cells connected in series, and each cell produces approximately 2 volts. We'll actually look at the half reactions and how many volts it actually produces. But if I multiply that by 6 of them connected in series, that gives me the 12 volts that a car battery or a lead storage battery gives off. Now these reactions are in your data booklet, so it's not something you have to memorize. But again, if I were to look at the half reactions and the net reaction happening here, and the voltages, so this was my cathode voltage is positive 1.68, and my anode voltage is negative 0.36. So when I take cathode minus anode, I get a voltage of positive 2.04. So about 2 volts, like I said. So when you multiply that by 6, you get your 12 volt battery. Okay? Fuel cells. Fuel cells are cells where the reactants are continuously supplied. A common type of fuel cell is a hydrogen-oxygen fuel cell, where hydrogen gas is pumped into the anode and oxygen gas is pumped into the cathode. Now, I actually have a diagram of this. I'm going to flip over to the diagram first. So this here is my anode. Hydrogen gas is being pumped in. This is my cathode. Oxygen gas is being pumped in. Okay? Now, if we look at those reactions, at the cathode, the oxygen is reacting with hydrogen ions and gaining 4 electrons to make water, whereas the anode hydrogen gas is producing the hydrogen ions that move over to the cathode and the electrons that the cathode needs to gain. So the net reaction that we have is water as a product, which makes a lot more environmentally friendly running of a machine. So this, you can have fuel cell operated vehicles, and so it's not producing carbon dioxide, which is a greenhouse gas, as we talked about in the thermochemistry unit. Okay, so if we look at this cell again, this is another diagram. We're showing the electrons again flowing from the anode to the cathode. Okay, and then as the hydrogen gas comes in, it gives off hydrogen ions and electrons that move to the cathode. And then the cathode again takes in that oxygen, electrons, and hydrogen ions, and water comes out as a product. Okay, as well as heat, power, and electricity. Now, the only problem is, in order to form hydrogen, we usually do it by converting methane or methanol into hydrogen, and carbon dioxide is a byproduct of that. So again, we are producing some carbon dioxide, but these fuel cell vehicles are a lot more efficient than a gas-powered vehicle, 24 to 32% efficient, whereas gas-powered cars are only 20% efficient. Now, here's a diagram of a dry cell cut open, okay? And you are given when it says the discharge of the cell, that means the operation of the cell. It means the cell is running, okay? Now, if I look at my net reaction, it looks pretty complicated. If I want to determine what's happening at the anode, what's happening at the cathode, the only way to determine it, even though, see, we're not told in the diagram which is the anode, which is the cathode, okay? We're told that we have cadmium and nickel NiO2, okay? So one of those is the anode and one of those is the cathode. Now, the only way to tell from the net reaction is oxidation numbers, okay? Whenever you have a balanced reaction and you're trying to determine what's the OA, what's the RA, your only step is oxidation numbers. So I have -2 for my oxygens. There's 2 oxygens, so that's going to add up to -4. The net of this has to be 0. So my nickel in this compound is +4. This is cadmium in its element form, so it's 0. Water's just there again to balance the hydrogens and oxygens like before. Then we have cadmium hydroxide. Now, hydroxide is just -1. I can treat the hydroxide as one whole thing. There's 2 hydroxides, so my cadmium here would become 2+, and my nickel, there's 2 hydroxides, would also be 2+, okay? So if I look at, again, what's happening with oxidation numbers, my cadmium in forming cadmium 2+ ions, the oxidation number is going up. So that's our Rallio, our anode, and the nickel is going from 4+ to 2+, its oxidation number is going down, so that's our O-GERC. Rallio up, the O-GERC. Okay, so the oxidation half reaction is my Rallio, that's what the O stands for there. And so it's cadmium making cadmium hydroxide, so it counts out those 2. Then we know that when you have an oxidation reaction, it's losing electrons. So electrons have to be on the product side, not the reactant side. So that's how we know the answer there is 1. And then the strongest oxidizing agent, that's the O-GERC. That's the NiO2. Okay? So the diagram doesn't really help us with anything. right? Doesn't tell us what's happening other than what the two reactants are, the cadmium and the NiO2. But then you have to use oxidation numbers to figure out what's happening, okay? There's one cell diagram. Here's another cell diagram where I have aluminum as one of my electrodes, and I have electrons flowing, so we know that's our anode because it goes anode to cathode. So this is my cathode, and if I were to look at what I have in my cathode, I have oxygen and water coming into the cathode. Hydroxide ions are coming out, so that means they're a product. So if I list everything that I have to find out my half reactions, we have aluminum solid, oxygen gas, and water. And so I want to find my SOA and my SRA. So my SRA would be the aluminum, but my SOA, actually, oxygen and water together are on that chart as a OA, and between that and just pure water, they're the SOA, okay? So if I were to write my reactions, my OGERC reaction is oxygen plus 2 waters plus 4 electrons is producing 4, I'm running out of space there, whoops, go back, 4 hydroxide ions, and my reducing agent losing electrons at the anode would just be the simple aluminum reaction where it forms aluminum ions, okay? So there's the hydroxide ions I said that were being produced, that this diagram is showing. They're coming out. Something going in is a reactant. Something going out is a product. Okay? Now they also have sodium hydroxide here as the electrolyte happening as the solution, right, to allow the ions to flow to complete the circuit. So in the aluminum air battery, the oxygen is acting as the oxidizing agent that is gaining electrons. So oxidizing agent gaining electrons. And the reduction half reaction, which is the same half reaction, is oxygen plus water and 4 electrons, making 4 hydroxide ions. Okay? So when you memorize Rallye-Awa, the OGERC, right, that answers a lot of these questions. So make sure you memorize those terms. And that is it for this lesson. Thank you for watching.